Okay, well, good morning, everyone. We're going to jump right in today and correct the homework question that I left you with last night, and then look at some more word problems. I'd also posted the or one of the homework sheets that I'm going to give to you to practice, and I'll probably go over a few of those questions today too. Kind of do two things at once, go through your homework with you, and introduce questions as well. So the question yesterday that I left you with is this one. Radioactive isotope, iodine 131. I'm not going to read the whole thing. Injected into the bloodstream. It's got a half-life of a certain amount, which is 8.2 days. And we talked about the general setup of all exponential word problem equations. And they're going to be variations of this form. They used AL here. I'm assuming, I'm not even sure what L stands for, to tell you the truth. It doesn't really say. I would have said like amount of iodine, so I'm almost wondering if that was supposed to be an I. But anyway, A0, and it's this funky looking zero here. I've heard this called A naught, as in the knot of a tree. You may have recently heard the topic of R naught when it comes to how viruses spread. So that's what the naught is. It's that little zero, which usually, in this case, means the starting value. 1/2 came as our B value. Now, I read today that there's a difference between the growth factor and the growth rate. This is called the growth factor. I always actually called it the growth rate, but it's called the growth factor. The rate is how much is the growth change from 100%. So this would actually be the growth rate, which is 50%, because you're losing 50% of the amount each time. So I'm going to try to get those two terms correct, but I may interchange them by accident. And our D value, 8.2, which is a division, because it's controlling the fact that this is decreasing every 8.2 days, but we needed to actually technically decrease every virtual day, let's say. So by dividing by 8.2, we're changing this quantity's amount every one value instead of every 8.2 days. But it's done mathematically in the table of values. So we have to divide by 8.2 to make that all work, which was really complicated to say, but it's based on yesterday's lesson. So hopefully that made some sense. There's a couple of things I wanted to talk about before I actually solve this question. It says, after how long should 25% of the iodine remain? And I mentioned the other day that, and you can see it right here in the B value, that when you're working with a percentage, you usually have to write it as a decimal in an equation. But this one, I did not. I just chose to leave it as 25. And because they didn't give us our original amount, I said we can use 100%. And again, I did not choose to write that as a decimal. So why is that? Why am I breaking the rules, or seemingly breaking the rules all of a sudden? Well, I'm not. And I'll show you what I mean. If I had chosen to write this as a decimal, and write this as a decimal, proportionally they're the same thing. Okay? I can multiply both of those sides by 100, because proportionally that gives the exact same answer. As long as you do the same thing on both sides, you're good to go. So, I mean, technically, I probably should have done this, because you're not supposed to use percentages. But I knew that because basically both sides proportionally are the same as this, I just left it like that to make it look a little bit more like the 25% that was there. But it doesn't really matter in this case, because it's proportional. Now, oops, I did not want to erase that. What's interesting is the first step in solving this. Oh, that would make sense, yes. AL is amount left, and A0 is amount at the original. Yeah, that would make sense. Thank you. I wasn't sure what the L stood for there, but probably left, so amount left. Okay, so as I was saying, what is our first step to isolating t? Because that's what I had asked you to do. Well, we're isolating a variable, so we have to work our way outside into the variable. The thing that's the furthest away from the variable is the 100. How do I get rid of the 100? Well, it's multiplying, so we're going to divide by 100. Well, as soon as I do that, and let me just write it quickly like this here, folks. As soon as I do that, I get this anyway. Okay? So that's what I was kind of saying, that it doesn't matter that I'm using 25% and not 0.25, because it's going to work out. As soon as I put the 100 here, it's going to work out anyway. Okay? Now, one thing I am going to do is I'm just going to erase this 1, because that's not there anymore. A 1 times anything doesn't change anything, so technically we can just go to this. Now, I'm going to do one thing, though. I am going to write this as a fraction, and there's a reason for that. Oops, wrong color. So 0.25 is 1/4. And just for fun, I'm going to go back to my sheep. Okay, so I'm replacing the t over 8.2 by my sheep that I've used in the past. Okay, so we're back to the situation where we're trying to get our bases to be the same, and then to drop the bases and to make our exponents the same. Okay, so it's dragon to the sheep is equal to dragon to the something, but these dragons aren't the same yet. And if you don't write it as a fraction, you may have missed that. If you went to 0.5 here, which is also a strategy that could have worked, you may not have seen that these two fractions actually have a way of turning into the same base. So 1/4 can just be written as 1/2 squared. Now, instead of using a sheep, I'm going to temporarily, and this is our variable substitution here, okay? I'm temporarily changing the t over 8.2, sorry, I'm having trouble scrolling here, the t over 8.2 into just a big X, just so that it doesn't look confusing for now, okay? It looks more like what we were doing before. And now I can just drop the bases. So we end up with x equals 2. Now it's x equals 2, but I'm going to write it like this. Actually, I'll change this to green just to keep the pattern going. Okay, so we just drop the bases and we say x equals 2, but we're not done yet. We're going to then replace the x by what we changed it from, which was t over 8.2. So if I do t over 8.2, where this one is, and now hopefully everybody can see where the 16.4 came from. So how do I get rid of that 8.2? It goes over to the other side, multiplies, and there's our 16.4. Okay, so this one worked out. I had said yesterday, I think, that you might need trial and error to figure this one out. And if you had gone to decimals, you might have needed to use trial and error to do it, at least to this point. But it still would have been pretty easy, since the answer was going to be 2, I think. But using the fraction versions of them really helps you see that the two bases can be written in a similar way. So I believe the prediction yesterday, calculated prediction, was 16.4, which is right here. So that is the correct answer. Okay, so we should have a sentence here. I'm not going to write the sentence, but it is a word problem. So after how long will 25% be remaining after 16.4? Now, what is the unit for time here? The unit for time is days. Okay, so it would be after 16.4 days. All right, which is a long time, right? And this is what I was talking about yesterday about athletes having to be careful about when they take medication, because if it takes 16.4 days before this happens, 25% of the substance is in the body. That means it's probably still detectable. Okay. All right, let's look at a couple of more examples. I'll pause for a second, though. Does anybody need me to explain anything more about this one? I'm not seeing any questions in chat. So let's keep going. Everybody can still hear me? Okay, good. These questions I took right out of your textbook here. So here's another one that deals with medicine. Okay, the biological half-life of thyroid hormone T4 is about 6.5 days. So here's another half-life question. And I'm concentrating on the half-life questions because they are a little bit more difficult, although I'm hoping they're starting to get less difficult now. And here's our lambda. Okay, so this is that lambda I was talking about. If a dose of T4 was not followed by repeat doses, what fraction of the original dose would remain in the body after 19.5 days? Now, I want you to notice that they actually didn't tell you what the original dose was. They just said if a dose of T4 was not followed by repeat doses. Now, what do they mean by not followed by repeat doses? Well, obviously if a doctor kept giving more of doses of this hormone, then it would be changing the math of the question. Okay, so it's like, here's the dose, let's walk away for a while and see what happens. All right, so you're not getting more and more doses of this treatment. Because they didn't give us the original dose, we're free to choose whatever number we want for that original dose. But the easiest value to use is either 1 or 100. Again, if we talk about our original dose, so we're going to call A0 100, meaning 100%. Okay, so, and be careful, this is not the percentage for the rate, okay? This is the percentage for our original amount. And you can use, and I'm going to write in brackets here, you can use 1 if you want, okay? It's your choice. So if they don't tell you what the original amount is, I like to use 100 because it reminds me that I'm starting with 100% of the material, okay? So what fraction of the original dose would remain in the body? Well, if I'm asking for an amount that would remain, I'm looking for my final amount, which I like to call A, okay? So I'll just write out the equation just so you see it again. We are dealing with half-life, so this is going to be 1/2, our B is going to be 1/2, and we're going to have T over lambda. And I'm going to write the lambda in, just so they start getting used to seeing that. And let's start putting the numbers in now. So we know we have 100% starting with, sorry, our 1/2. Now our time, and I'll use color here, it says 19.5 days. Okay, so that's going to be our T value. And I'm dividing that by our D value. I'm going to use red for that. And our D value, or sorry, our lambda value is 6.5 days. And again, just to belabor this point, because if you need a deeper understanding of how this works, 19.5 days divided by 6.5 tells us how many 6.5 day periods are there in 19.5 days, because that's what we're interested in. In other words, how many half-lives have occurred in 19.5 days. So this division tells you that. Okay? I hope that's okay. So now we're just typing this into a calculator. I'm going to do that off screen so I don't have to keep switching screens, and if somebody can double check and make sure that I didn't make a mistake. And I forgot to write the bracket around the 19.5 over 6.5. I'll do that in a second. And I'm getting 12.5 as my final answer. And 12.5 looks like it's good. Okay, so now this 12.5 is based off of our 100. So technically this is a percentage. There's 12.5% left from the 100% that we started with. Okay, And like I said, I'm hoping that you're starting to see that if you can understand why this is 1/2 and where the, why do we have a lambda? We have a lambda because the change is not happening every hour. It's happening, or every day in this case, it's happening every 6.5 days. Okay? We will see some examples where this will just be a 1, but these are the harder ones. So if you can understand the harder ones, the easier ones should be easy. Now that was question A. Question B says, how long would it take until only 6.25% of the original dose would remain in the body? So what is this quantity? This is not lambda. This is a final amount. Okay? So how long is a time value? So we're looking to, and I'm trying to break down the word problem here, so because a lot of students get really upset about word problems, but if you break it down into little pieces, so how long is a time value? So we're looking for a time value in this question. Well, where is the time value in our equation? The time value is up in the exponent. Right? So we're going to have to isolate that exponent. So this is very similar to the question we just did on the previous slide. So we just need to make sure we put all of the other numbers in the right place. So if this is our final amount, 6.25, let's highlight that in blue. Okay, so 6.25 is my final amount, and it is a percentage, so I could write it as 0.0625, but it just becomes cumbersome if you do that. And if you understand that this is the final amount, and that the original amount is still considered to be 100, then these two are going to proportionally become 0.0625 anyway. Okay, so I like to use those original percentages, even though we're not supposed to, but it's going to work out, so it doesn't matter. Let's keep this as 1/2 t over 6.5. So again, the first thing we're going to do is divide by 100, which I'm not going to write down. You should be able to follow that. So the decimal place moves 2 spaces to the left. Sorry, I'm thinking about something here. The 100's gone. And at this, I think this actually could be written as a fraction. Anyway, I'm going to show you an example of which way, what you would do, if we decided to write it as a decimal. Okay, so let's say we decided to write it as a decimal. So because I'm deciding to write this as a decimal, I'm going to replace that as a decimal. Yeah, somebody figured out, I think, what this fraction is as a fraction. Some of you may not be able to recognize that, though. So let's just go to the decimal value. It'll work out anyway. And I'm going to do my sheep substitution, which I'm just going to call an x substitution. Okay? So I'm going to say that x is equal to t over 6.5. Just to, and you don't have to do that. If you start to get comfortable with this, you can just leave it as that. But I find it helps me to see, okay, what am I doing here? Now, just for fun, we learned about scientific notation the other day, right? Let's write this decimal in scientific notation. So I need the decimal to be here, but it's supposed to be 2 steps to the left from that position. So I need to make a 10 power here that moves the decimal 2 steps to the left. And as I showed last week, that becomes a -2. Now, I'm just doing this for fun, okay? I'm just doing this for fun. So we don't have to do that. We are going to be looking for this on our calculator, but I just wanted to show you that you can actually write it as a scientific notation, okay? So let's take a calculator out and start doing trial and error. And we have to do trial and error here until we can get to 0.0625, okay? So I'm going to show you my calculator screen here. So hopefully everybody can see that. Sorry, I'm just moving things around on my screen here, folks, and I'm having a little bit of trouble. And I just opened a program that I don't need. Okay, this is only supposed to happen on Mondays. All right, so we've got 0.5, and we've got to raise that to a power that gives us 0.0625. And it looks like somebody's already gotten the answer in chat. Let's just show, you know, what a student would do. So, I don't know, let's raise it to the power of 3. Well, that's too small. Let's raise it to the power of, I don't know, 10. Well, that's a lot smaller. But we need it to be smaller than our original one. Okay, it's just way too small now. So it's somewhere between 3 and 10, right? What if we went to the power of 5? Okay, well, that's still too small. So now it's somewhere between, so power of 3 was 0.125, which was too big, and power of 5 was too small. So let's try 0.5, as was suggested, to the power of 4. And that gives our exact answer. Okay, so going back to our Smart Notebook file here. So we know that through trial and error, x is equal to 4. Okay, so if x is equal to 4, well, I'm not looking for x. I did a variable substitution. I've got to go back to my original variables here. So t over 6.5 is equal to 4. That means t is equal to 4 times 6.5. And using a little bit of mental math here without needing a calculator, it's distributivity, right? So we can consider this as 4 times 6 plus 0.5. So 4 times 6 is 24. 4 times 0.5 is 2. So I believe it's 26. Okay. So that is the answer. Now, what is the unit here? Let's go back up. Time is in days. So this would be 26 days. All right, for us to get to that fraction. So again, I'm hoping with successive examples that are similar to each other that you're starting to get a feel for how this works. We've actually, you know, even gone a little bit beyond and started isolating the exponent. I want to do something with you right now, and I want to introduce the topic of a logarithm. Now, we are actually going to study, I think I spelled that right, logarithm. Yeah. We're going to study logarithms in more detail. I'm actually starting you at the end of the story. There's quite a long story, at least 2 days of lessons, to explain how this story ends this way. But this is the most powerful part of the story anyway. So I'm going to go back to this line right here, okay? So 0.0625 is equal to 0.5 to the x. We'll leave it as x for now, all right? What does a logarithm do? Well, a logarithm is an inverse function of an exponential. But there's a whole bunch of rules for logarithms that state what kind of base does the logarithm have. So a logarithm symbol, by the way, is log. And you can have all kinds of bases for logarithms, all right? The most common base for a logarithm is a base 10. And on your calculator, that's just written as the button log. Okay? But you can have a log base 2, you can have a log base 3, you can have a log base whatever. There's another special logarithm button on your calculator, which a lot of students mistakenly think is IN. This is actually LN. Okay? It's called the natural logarithm, and it's got a base, a special number that we haven't seen yet, which is E, which is a constant in mathematics. Okay? LN is the only real log. Yes, eventually it will be for sure. But we're going to use log base 10 mostly this year because I don't know if we're going to be able to get to explaining what base E is. Okay? That's a calculus concept. I might get somewhere close to that, but I don't know how close we'll get. Anyway, I digress. So what does a logarithm do? It's an anti-exponential. It destroys an exponent and gives you it destroys an exponential and gives you an exponent. But I'm skipping a whole bunch of steps here. All right. I'm just going to show you how a logarithm works in a case like this, and we'll explain how later. All right. If you needed to calculate this without trial and error, and this one worked out nice because we got a really nice answer of 4, but if I had changed this number to anything else, it would be a little bit harder to do. If I put a log base 10 in front of both sides, like so. What this logarithm does on this side, and this is the side that we're interested in because we're trying to isolate x, and x is in one of the absolute worst positions it can be in to isolate. How do you pull an x out of an exponent and move it so that it's next to the equal sign isolated? Okay? Well, I like to call this, and I've heard it called different things, I like to call this the down and front rule. Some people call it the cherry picking rule, I think it's been called before. What a logarithm does is it pulls an exponent down in front of the equation on that side. So just to save me some time here, I'm just going to put actually, I better not do that. I am going to need all of this. Sorry. So the x that was up here comes down in front, effectively putting it next to the equal sign, which is where we need it to be able to isolate it. And the beautiful thing about this is your calculator has a logarithm button. This is the log base 10, which is the main logarithm button. So if you just consider this as a function, like square root of 0.5 or 0.5 squared, it's just a thing multiplying x. How do we get rid of things that are multiplying? Well, we divide them on both sides. So I'm going to divide by log base 5 on this side, which is going to eliminate the log base 5 because that divided by that is just 1. And I'm going to divide by log base 5 on this, log of 0.5. I think I was saying that wrong. Log base 10 of 0.5, log base 10 of 0.5. So I'm dividing both sides by log base 10 of 0.5. I'm getting excited, folks. This is fun stuff for me. So log of 0.0625 divided by log of 0.5 equals x. Okay? Now we already know that the answer for x is supposed to be 4. Well, on your calculators, and I'm going to show this, let's do so there is a log button right here. Let me clear this. I actually want to delete the history as well, so we just see this. So I think I can do... Oh, okay. So this calculator is a little bit weird, folks. I have to put the number in, so the 0.0625, before I press the log button. Some of your older calculators might be like that as well. If you can see log on your calculator screen when you type or when you hit that button, then you can do it first. But this calculator has to be done second. So I'm going to do the log of that, and I'm going to divide that by 0.5 log. Oh, look at what we get. We get the same answer that we had before. Trial and error. Now we get it mathematically. So that's the beautiful thing about a logarithm, is it allows us to actually solve for an exponent by using this down in front rule. Let me scroll up a little bit. I hope I didn't blow anybody's ears out there. But this is so exciting. We can bring that exponent down in front. We can solve all these questions now, even the ones that are difficult where we have to use trial and error. Now we don't have to. And I'm going to hopefully within the next couple of days, somebody just said I just fired them up in chat, which is great because this is fantastic stuff. Yeah, so x is equal to 4. And we can get the exact same answer as before, okay? So this opens up so many things for us in the future for being able to solve questions like how long does it take for something to happen instead of just what is the final answer. So, whew, great stuff there. Okay, so I will get back to logarithms. I'm not expecting you to understand how this works. It sounds like some of you do, okay? But yeah, if you put a log in front of both sides, that exponent comes down in front, okay? Awesome stuff. Okay, so moving on to the next example. So here's another, a completely different topic, all right? So this is not medicine or half-life even. So the percent of sunlight, S, that reaches a scuba diver underwater can be modeled by this equation. Now, I'm expecting that whoever wrote this textbook did some research and that this is the actual equation for how sunlight slowly disappears as you lower into the depths of water, okay? So 0.8 D times 100%. Now, I actually don't like how that's written, however, because your 100% should be your A0, and this should be second, in my opinion, okay? So I would have written it like that. And I'm going to get rid of the percentage signs just so it doesn't mess us up, okay? We're just using 100 as our starting amount here, all right? At what depth does 64% of the sunlight reach the diver? Now, before I get to that, let's talk about the difference between decay factor in this case, because this is a smaller number than 1, which means we're losing sunlight, okay? So decay factor and decay rate. If I ask you what is the decay factor, the word factor means things that multiply, that would be 0.8. But if I ask you what is the decay rate, can somebody in chat tell me, and you can all answer if you'd like, if you know the answer, what would be the decay rate in this case? In other words, by how much is the sunlight decreasing as a percentage or as a decimal as we go down into the depths? I'm not getting any answers. Let me give you a hint. Remember that B is always based on 100%. And somebody's got it. So if this number is based on 100%, now, and this is where things get a little confusing, and I hope I'm not going to overly confuse things by trying to explain this. This 100% is not the same as this 100%, okay? This 100% is replacing an unknown starting amount. This 100% is telling us what is our growth factor changing by, okay? So how did I get 0.8 from 100%? Well, what percentage would 0.8 be? 0.8 is 80%. Well, if I started with 100, how much did I lose? I lost 20% to get to 80%. So my decay rate is 20%. And I know that's confusing, okay? The decay factor is 0.8. That's what we put here. But the actual rate of decay is how much of the water block the sunlight. Well, it's blocking the sunlight by 20% as you go down. Every, is it, I don't know, do they have, yeah, it's in meters. So every meter you go down, okay, you're blocking the sun by 20%. That might make more sense when we see some more decay questions in the questions that I have coming up. For question A, at what depth does 64% of the sunlight reach the diver? Well, this would be the final percentage, the final amount, which is S. Okay, so I'm going to put 64 in that position, the final amount position, equals 100. Now, to save us some time, we're always going to be dividing by 100 in cases like this, right? So let's just do that right off the bat, all right? Some of you may have been clamoring for me to do that already. And now we've got to find D. Now, you might be saying, hey, this is another logarithm scenario. It certainly is, but how easy is it to get 60.64 from 0.8? So this is actually a scenario where trial and error, it's not technically trial and error because we can easily change 0.64 into 0.8 because 0.8 squared is 0.64. It's like 8 squared is 64, right? Proportionally. Okay, all of a sudden I'm doubting myself. That is correct, right? 0.8 squared is 0.64. Okay, just making sure. I don't know why. My brain just said, wait a second, that might not be right. So, drop the bases. D equals 2. Okay? So, this won't always happen. It won't always be easy like this, where you can change one side's base into the other. And that's why we're going to need a logarithm. But this one works quite well. We drop the bases, and we get D is equal to 2. So after 2 meters, if we answer the question, at a depth of 2 meters, we end up with 64% of the sunlight reaching the diver. What percent of sunlight reaches the diver at a depth of 10 meters to the nearest percent? Folks, I'm going to leave that up to you to maybe look into yourselves. This is out of your textbook. I think it's actually a solved question, if I'm not mistaken. No, it's actually a question out of the textbook. But this is simple. This is just, here's the depth, which is your D value, right? Just sub that in and do the calculations. So I'm going to skip that one and move on to our other examples. So I have the assignment open. I'm just going to have to do something to bring the questions into the Smart Notebook program here. So just give me one quick second. Now, as teachers, we help each other out quite often. I'm not the one who wrote this question, so even though I probably would have used my own name in a question anyway, this was another teacher that had developed this worksheet, and I just stole it from her. So here's another example of a type of exponential question. And it is a growth. So I'll read the question. It says, Mr. Conrad has $400 right now. His super awesome savings account pays 12% interest per year. Not only is this an exponential question, it's also a finance question, which is actually the next unit after this one usually. Although I don't think I'm going to be doing that unit next. But anyway, this is a finance question. This is a compound, what we call compound interest. Which is the way that everybody on the planet is going to try to save money for their retirement. You're going to put money in the bank and you're going to try to get some compound interest off of it. And what compound interest means is that $400 is going to gain interest over a certain amount of time, and this is per year. And then the next year after that, you're going to make money on the $400 plus whatever the interest was on the previous year. So you gain interest on your interest, which is compound interest. Okay? So question number 1A is, what is the growth rate? Now, I made a difference between the word growth rate and growth factor, and I actually want to know both of these. Okay? So the growth rate is what it's increasing by, which is just 12%, which we can write as a decimal. Okay? Now, what is the growth factor? The growth factor is 100 plus 12%. As I showed the other day, this is your B value. Okay? So you always have to calculate what it is with respect to 100%. So this is 112%, which is 1.12. So that is our B value, which is our growth factor. Okay? How much will Mr. Conrad have in 10 years? Let's set up our equation. Now, this one, we're going to have to talk about the per year and our D value. Okay? We've been seeing a lot of questions recently about half-life where it isn't changing after 1, 2, 3, 4, 5 years. This one is. So if it's per year, what is our D value? It is 1. So our formula is a little bit easier, and I'm going to use A. I like the letter A. The word amount can relate to a lot of different things. If it was a population, I would change it to P, okay? But for money values, I find the word amount works well as for other things, so I'm just going to keep using A. So I'm going to write the formula without putting any numbers in it. And I'm not going to put a D here, okay? Because D is 1, why write it? Dividing by 1 doesn't change anything, okay? So this is actually often the form of the equation that most teachers will start by showing, and they'll only introduce the D later. I sometimes like to show the harder questions first. Like I said, if you know the harder questions, then the easier questions are just easier, okay? So we're just subbing in after 10 years. So our initial amount was $400. Our growth factor is 1.12, and our power is 10. And I'm going to let chat figure this one out for me, and I'm going to trust that your answer is correct. Don't let me down, chat. Can I get confirmation? So 1242.34. So here's an interesting little discussion. How many significant figures should this answer have? Science topic. We don't usually force this in math. Eventually we do, okay? But how many significant figures or significant digits should this answer have? My lowest number of digits is 12. There's 2 digits in the number 12. There's 3 digits in 400. Not 2 decimals, 2 digits. Okay, so be very careful about this. Yes, it's a money value, okay? But technically speaking, your final answer can't be more precise than any of the numbers you used in the original question. So technically speaking, because 12% only has 2 digits, I can't write this precisely to this much precision. This is only supposed to have 2 digits, and this is what you're going to have to think about in science when you do significant digits, okay? My answer can't be more precise than the numbers I used to create it. So the correct way to answer this would be 1.2 times 10 to the 123 dollars. Technically speaking, that's the correct way of writing that answer, and that's why you're going to need scientific notation. Okay? So I'm not going to talk about that more because I'm just giving you extra information because it's fun. But I will accept this is the correct answer in math, all right? But this would be how you'd have to write the answer in science. That's why all those answer keys are all messed up in science textbooks. They're not messed up. They're done correctly. If this is what you mean by the answers are messed up, that they're in this form, that's the form they're supposed to be in, all right? And there's all kinds of rules about significant digits. So anyway, let's move on to question C. And I know I'm speeding things up here, but I'm like, this question was just substituting 10 into the question. So one thing I probably should have checked, everything is in years. Okay, so we didn't have to do, be careful folks. They'll sometimes throw stuff at you where they'll say per year, and then this will be per day. And then you have to do that kind of conversion. Okay, so that I'm going to let you discover fun stuff on your own, those fun things on your own. So when will Mr. Conrad have $1,500? When? When is a time value? Okay, so now all of a sudden I'm going to be looking for the t value in my exponent. I may need trial and error. We may need logarithms. We'll see. All right. So $1,500 is my final amount this time. When will I have that final amount? So final amount goes first in the equation. Everything else is the same, but we don't know our t this time. So now we have to isolate for t. Okay, well, what's the first step? Well, I know probably everybody knows this, so I'm just going to go ahead if that's okay. We're going to divide by 400. All right, so if I divide by 400, what's be 15 divided by 4? I'm trying to do this in my head. 15 divided by 2 is 7.5. 7.5 divided by 2. Yeah, so what is 7.5 divided by 2? My brain just stopped working. Or just tell me what 15 divided by 4 is. 3.75. Okay, thank you. Thank you. It's funny how sometimes you'll just block when you're teaching stuff, your brain just blocks. Anyway. Okay, so we have that. Now, trial and error, right? But I just showed you a really cool new tool. So let's use that new tool. Let's put the logarithm in front of both sides. Okay? Now, this is not a multiplication, all right? This is like square rooting. When you square root something, the function has enveloped that side. Okay, it's swallowed it up. So you can't just separate these anymore. What it does is it brings the t down in front. So we end up with t log 1.12 equals log 3.75. And now I'm going to divide, oops, sorry about that. Now I'm going to divide both sides by log 0.12. So we're going to have log 3.75 divided by log of 1.12 equals t. And if you do that on your calculator, you will get your answer. And I'm going to let you do that. Okay? So practice 11.66. Double check that. Okay? And the last question, when did Mr. Conrad have $300 in his account? That a when question is still a time confirmed? Okay, great, for this one. So a when question is a time question. Folks, I feel like you're ready to start doing these. So here's what I would like to do. And this is going to just give me a second here. I wonder if I can show the whole page to everybody. Give me 1 second. I don't know how clear this is going to be, because I had to make it small so that everybody could see it, or sorry, so you could see the entire page. Okay, so this is the assignment from yesterday. Okay. So I just want to read through a few of them. We're starting to run out of time here for what I like to go for my time limit, I should say. So Carrick's Pokemon collection is worth $250 right now. Its value depreciates by 18%. So this one was an increasing example. 2 is a decreasing example. My growth rate is, sorry, my decay rate is 18%. Because this is depreciating, it is decaying in value. So my decay rate is 18%. What would my B value be? B is 100% minus 18% this time, which we were doing for Half-Life. We were subtracting 50%. This is another scenario similar to Half-Life because it's depreciating, which means decay. All right? So I'm going to do 100 minus 18%, which gives 82%. And think about it this way. If you lose 18%, what percentage do you have left? You have 82% left. Okay, so that's the way you've got to think about that. How much will the collection be worth in 5 years? State the domain and range. Those are questions you now should be able to answer. For question 3, the formula is given to you. Now, interesting part to question 3 is B. It says, when will the population be double? And for some reason, I've had students get confused with what to do with that. Well, that's because they don't understand what the original population is. Now, be careful here. This is your original population, 29.6, but this is a population in millions, okay? So it actually means 29.6 times a million, all right? But if the population doubles, what is going to be your final population? Well, you just multiply that by 2, right? So those are the types of wordy problems that are going to come up. Is what does it mean by doubling? If this had been triple, I would triple my population, right? And the word double will come up in other scenarios too. But anyway, I'll let you discover that a little bit on your own too. A colony of 20 bacteria doubles in size every 20 minutes. Okay? And I'm going to talk about this one because I just mentioned, that I'm going to let you discover it on your own, but I don't think I'm going to do that because it's right here. Okay? This double is different than this double. This is the population doubling from an initial population. This is saying that 20 bacteria double in size every 20 minutes. This double is actually your B value. Very subtle difference there. Okay, your B value in question 3 is 1.0124. What is the B value going to be in question 4? That's right. Because this double is actually your growth factor, it is still based on 100%, but this time we're not subtracting or adding anything from 100%. We're actually multiplying by double, which is 200%. You're getting 200% of the bacteria every 20 minutes. 200% as a decimal is 2. So it's a very subtle difference. When will the population be double? Given this growth factor, a population doubles. It's a very subtle difference. I can't state that enough, okay? So in this case, the doubling actually has to do with the population, which is your final amount. In this case, the doubling has to do with what your actual growth factor is, okay? Every 20 minutes is your D value. So notice the difference between a d-value that's a number and a d-value that's 1. Okay? I believe this question says every year. Okay? So every year is a d-value of 1. Per year is a d-value of 1. Every 20 minutes is a d-value of 20. Look at this problem. And I told you this was coming. Okay? There's an hour here. There's 20 minutes there. You can't have 2 units like that in the same question. So you're going to have to convert one into the other. So I don't know if you can tell how excited I am for you folks to be doing these kinds of questions. But we're going to finish the lesson there, and that's going to be your homework to do, okay?